Okay, so thank you. I'd like to thank the organizer for the invitation. It's always a great pleasure to be here. So I'll be talking about some joint work with Vadim Kaloshin. So still pretty much in progress. I'm going to speak about what we have done so far. And so it concerns the problem of so-called Arnold diffusion. But so I'll be a bit more precise about what is these questions. So let me start by describing the setting. So it's a classical setting of Hamiltonian perturbation theory. So I will denote by Tn will be the n-dimensional torus. I take B, an open ball of Rn, and I consider a function, so capital H, it will be Hamiltonian, which is defined on the product, so Tn times B. So it's a real valued function, and unless stated otherwise, it will be real analytic. I mean, at least I will need a lot of regularity for what I'm going to speak about. So once you have a function like this, you can define a system of differential equations. So this is the system. Okay, so I associate it to capital H. So first of all, this is my phase space, so I will denote the variables by theta and I. I will call theta angle, and for some reason I will call this variable I action. So it lives in the product, so Tn times B. So this is a vector. Okay. So to a function capital H, I will associate this system of differential equation. So it's theta dot is equals to the partial derivative of capital H with respect to y, with respect to I, and I dot is minus partial derivative of capital H with respect to theta. So that's a Hamiltonian system. Okay. And I will consider capital H, so my Hamiltonian of a special form. So I will consider a function that can be written as sum of two Hamiltonians. So the first one I will call small h. It depends only on the I variables, so only on the action variables. And the second Hamiltonian, I will call it small f. So it's epsilon small f. So f is a general term, so it depends on all the variables. But I have an epsilon in front, and it will be a small parameter. So I will be interested in this type of system with this type of Hamiltonian with epsilon small. Okay. So if I put epsilon equals to 0, okay, you just, in this case, capital H is just small h, I can solve this system of equations. And all solutions, they are quasi-periodic, okay? Which means, so first of all, it's easy to see that since small h does not depend on theta, so the speed of the action variable is equals to 0, so they are first integral. So in the flow, when I have I of t is always equals to I of 0. And for theta, now you can see easily for capital H equal to small h. So here it's a constant vector, okay, which means that the evolution of theta, I mean, is linear. Okay, theta of t is equal to theta of 0 plus t times some vector. And this vector is given by the gradient of h applied to the point, to the initial action I'm starting. Okay. So that's all solutions are like this. Okay. So to put it differently, I can say that given any I prime in B, if I consider the set of I which is equal to I prime, it's an invariant torus which is quasi-periodic. So invariant torus because this is an invariant set, and this is like this is a torus. I mean, homomorph. I mean, it's like exactly a torus, and the flow on this torus is given by a linear flow, by this. Let's say that the flow of translation or rotation. Okay? So that's what I have for epsilon equals to 0. Now, of course, the question is easy. What happened for epsilon non-zero? So now for the rest of the talk, I will be interested for non-zero epsilon. Okay? So in this case, there was a conjecture by Arnold a long time ago already. So let me put the statement already. So I wrote Arnold in the 60s. Actually, this is what exactly Arnold wrote, but not in the 60s. So many different forms of the conjecture. He wrote many different forms. That's the most precise I found. And he wrote this, I think, in '92 in some proceedings. So the conjecture, it goes as follows. So I recall from the beginning, now let me just say something. So I would consider capital H This will be the integrable part. This will be the perturbation. Okay, I will keep this notation, small h, small f. Okay, so the conjecture is as follows, so I will read it. So assume that h is generic and n bigger than 3. Then, given any 2 points, I prime and I second, on the connected level hypersurface of H in the action space, there exist orbits connecting an arbitrarily small neighborhood of the torus I equals I prime with an arbitrarily small neighborhood of the torus I equals I second, provided that epsilon is non-zero, is sufficiently small, and that F is generic. So it's, I don't know if it's a clear conjecture, but at least in this one, he has, so I put in red here that he has this for a generic perturbation and for a generic integrable Hamiltonian. Okay? So I will make a reformulation of this conjecture. So this is a kind of instability. So this essentially means, it means that given any delta, strictly positive, for epsilon sufficiently small with respect to delta, okay, then the Hamiltonian flow, when you restrict it to an energy level and you project onto the action space, its delta has orbits which are delta dense. Okay? So it's a kind of delta transitivity, of course with certain restrictions. So you have to restrict to an energy level and to project onto the space of action. So this is what Arnold asked. Okay? I mean, this is what he asked exactly. This is essentially what I understand of that. So I'll try to make a translation. And so if you want to compare, so this is not, so it's a kind of delta transitivity. Okay, so it's not transitivity. It doesn't ask for dense orbit. Of course, that's possible. Okay, you can ask more. You can ask that the flow has an orbit which is dense in an energy level. But here, of course, if you let delta goes to 0, this can goes to 0, and so this does not make sense. Okay? So this is a much more complicated problem to ask for transitivity. Okay? It's pretty much out of reach for the moment, I guess. And this actually also is pretty much out of reach in this generality, but I'll be discussing that. So this is kind of a weak transitivity, if you want. But this is already complicated, so you can ask for a weaker instability. Okay? So what is the weak instability in this case will be to find one orbit, okay? A time, which will depend on epsilon, and a constant c independent of epsilon, such that this, the variation of the action is bigger than this constant. So it's bigger than some constant independent of epsilon. Okay? It's over order 1. Here, in this conjecture, means that if you are given any 2 points, you can find one orbit that connect arbitrarily small neighborhood. Here, you just say, I have one orbit that can move a little. Okay, that's much weaker, and that, well, it's called like a drifting orbit. Okay, so these are just conjecture, and I will explain what is known and what I'm interested in this problem. So maybe this last 10 years, there will be a lot of effort of trying to improve that. So I will state later, but Arnold gave an example of such things, actually an example of weak instability for one H and one specific F. And there have been a lot of efforts to try to have like a generic perturbation. Okay? And so this is a complicated problem, but perhaps trying to have like a generic integrable Hamiltonian is as complicated, or maybe even more complicated than that. That will be my point in the talk. So now let me explain what this is why this is complicated, or this is complicated. Because so it's a kind of conjecture about instability of certain Hamiltonian system. In fact, it's a long time we know that these systems have some kind of stability also. So there's a competition between stability and instability. Both phenomenon coexist, should coexist if we believe the conjecture. So first of all, let me speak about some consequence of KM theory. So I will call this infinite stability. So this requires some assumptions on the integrable Hamiltonian on small h, some generic assumption on small h. So you can have various one. But so the result of stability I'm going to discuss are valid for any perturbation. Okay? And of course, conjecture of instability cannot be true for any perturbation, because you can have perturbation that keeps the system integrable. So You have to put condition on the perturbation. Okay? So let me say that the integrable Hamiltonian H is Kolmogorov non-degenerate if this is the Hessian matrix, if its determinant is non-zero at all points. Okay? Which means that the gradient map of H is a local diffeomorphisms at all points. Okay? Once you make this condition, once you assume this condition, there's a theorem by Kolmogorov which says that many tori persist, so I will not write precisely the result. I will just explain the consequence of preservation of invariant tori, or preservation of quasi-periodic solution. Is that, so if you assume H is Kolmogorov non-degenerate, then for any n bigger than 2 and any f, so it's true for any perturbation, what you have is that most solutions are stable, provided epsilon is small enough. So, which means, so this most is a set of positive measure, and the measure of the complement goes to 0 when epsilon goes to 0, so it's a set of big measure, let's say. And what is stable here? So it's like unstable, there's no precise definition. Here stable, it means that for most initial action, or most initial point, if you take the solution, then the action variables, they have small variation for all time. So for all time, it's smaller, so I put this symbol here to say that there's some constant independent of epsilon and so on. So the variation is smaller than square root of epsilon for all time. Okay? So for these solutions, you cannot, they are not unstable, they are stable. You cannot have the instability as Arnold asked for this solution. Okay? So this is for most, but not for all, of course. And the complement of this can be very big, can be dense, for example. Okay? So that's the first restriction on trying to prove maybe not the conjecture of Arnold, or to prove something weaker, to show some instability. Now there's a second, let me put a second restriction. It comes also from KM theory, but a different variant. So now I introduce another non-degeneracy assumption on H. So I will call it Arnold non-degenerate if this determinant is non-vanishing at every point. So what is this determinant? So here it's a n times n square matrix. Here it's a n plus 1 times n plus 1 matrix. So here is n times n, and here I have a line, and here I have a column. Here I have a row, here I have a column. Here I put just 1, 0. Okay? So if you assume that this determinant is non-zero at any point, then what you can prove, in fact, you have preservation of invariant tori also, but slightly different than the result of Kolmogorov, because with these assumptions you can prove that this family of invariant tori, they are inside the same energy level. Okay? That's a non-degenerate, this is called isoenergetically non-degenerate. Okay? So then you have a conclusion like this, but so now a small part of the conclusion, so this was proved by Arnold, still in the 60s, is that, so assume H is Arnold non-degenerate. So of course there's a result for any n, but now let me just say what is important from this, is that for n equals 2, okay, and any f, then all solutions are stable. Okay? Provided epsilon is small enough. Means that all solutions satisfies this estimate. Means that the action, they cannot vary a lot. Okay? So that's why in the conjecture of Arnold, he asked already n bigger than 3, because this is like, for him it's generic. So if you don't assume that, of course you can have diffusion already starting, instability starting n equals to 2. So these are a first type of restriction on instability, because a lot of solutions, and sometimes all of them, so of course it depends on condition on the integrable part, okay? And these are independent of each other. This does not imply this, and this does not imply this also, okay? So now a second restriction, it comes from the fact that, okay, maybe you don't have this for all time, but you can have this for very long time. Maybe not for all time, but for very large interval of time, which makes that maybe the solution can be unstable, but if it's unstable, it's after a very long time. So you need to be able to observe your solution for a very long time, which makes the problem more complicated, of course. So I will call this effective stability. So it's around the Nekoroshev theorem. So let me introduce where does this come from. So first of all, you have some trivial stability estimates. Okay? if you take for all H, so for all integrable part and for all perturbation and for all solutions, you have this. Okay? Given any rho positive, then the variation is at most rho for this time interval. Okay? Which means that, put it differently, it means that the speed of, if you consider the evolution of this action variable, the speed is at most epsilon. So it's slow, it's at most epsilon. Okay? So this is true without any assumptions. Now let me introduce another definition. So it's very informal. You see, I can make it formal, but it takes a long time to make this formal. So I would say that the integrable Hamiltonian is effectively stable if you can do better than this. Okay, so I just put it like this, which means, so let me say let's define a Hamiltonian which is not effectively stable, and then the definition of effectively stable would be the negation of that. A Hamiltonian which is not effectively stable, it means that H, okay, it means that you can find one perturbation and one solution for which this inequality are equality, which means that the speed is exactly epsilon. Okay? So this is what I mean by effectively stable, what I mean by not effectively stable. By effectively stable means I have this for a longer period of time. So here it's for a period of time which is of order 1 epsilon. So if epsilon is small, this is big. But maybe I can do for even a longer time interval. Okay? So now I will put another, again, definition. So there will be various definitions about the integrable Hamiltonian. So I already defined what is called Mogorov non-degenerate, what is Arnold non-degenerate. Now I have effectively stable, and now let me define what is a steep Hamiltonian, or Nekhoroshev non-degenerate, because this was introduced by Nekhoroshev, not in this form, but this is an equivalent form. Okay? So the Hamiltonian is steep if for any point here in B, for all vector subspace F, okay, then you look at this affine subspace, so I plus F. Then if you take your integrable Hamiltonian H and you restrict it to this affine subspace, you ask that this function, so this restriction, has only isolated critical point. Okay? Well, that's a definition. In fact, that's a complicated definition if you try to work with that, but so I'll come to this point. Okay, what's the purpose of this definition? Because so what Nekhoroshev proved, in fact, if your H is steep, then it's effectively stable. In fact, it's much more than effectively stable. You have much better than this. Okay, this is what he proved. So assume H is steep, then for any n bigger than 2 and any f, of course, I always put n equals 2 because z equals 1, there's nothing to say about that. Okay? And for any f, all solutions they satisfy, so I have all my solutions. So this is for all solutions. I recall that consequence of Km theorem gives this for a lot of solutions, but not all of them. Okay? So for all solutions, the variation of the action are small for an interval, for a time interval. Oops. It's not working. Right? Okay, sorry. So the variation of the action is small for a time interval which is exponentially large with respect to the inverse of epsilon. So I put it like this, so it means, so here I have epsilon to some exponent, b, okay, some constant. Here I have this comes from the trivial estimate if you want, but now I can put even an exponentially long factor, so in fact the variation is small for very long time. So of course for this solution they can become, so okay, you can have a large drift, but after a very long time. Okay? This does not mean they are stable. I mean, these solutions, because this is true for all solutions.
What's the regularity?
Analytic. So if it's of finite differentiability, if it's CK, for example, then you replace the exponential by some power, which depends on the regularity. Okay? And if it's, so if it's smooth, to infinity, this is like bigger than any power of 1 over epsilon. And if it's like you have some intermediate regularity, like if you have a certain growth on the derivative, if it's infinity and you have a certain growth on the derivative, then what you have here is related to the growth of this derivative. So this is for analytic system. So this, This puts more restriction again on finding unstable solution. Okay. Now let me discuss a bit more about, because so I guess the first condition about a non-vanishing of determinant is a bit clear. I mean, this is a nice definition, nice condition you can put on the integrable part. This already is a bit like, is a bit ugly actually. So let me discuss a bit this notion of steepness. So first of all, so I can give some example of steepness, but by the way, not too much actually. So the main example and the only one which are well understood are convex or quasi-convex functions. So if you take a convex function, which means that the Hessian is positive definite, okay, and quasi-convex, so it's a mild generalization, well, depending on how you define it, but because sometimes you ask for quasi-convex function not to have critical point, but sometimes you can allow them. It means that this matrix, or this quadratic form is positive definite when restricted to the orthogonal complement of this vector. Okay, so this is a n-1 dimensional subspace. Okay, so these two classes of functions, they are steep. Okay, and these are, and by the way, so this convex function, if you want to relate them to Km, this convex function are Kolmogorov non-degenerate, and this quasi-convex function, if you add the fact that it has no critical point, it's Arnold non-degenerate. Okay. And I would say that these are the only well-understood steep function. So I will be speaking a bit about that. So here's an example of convex function. So I just want you to give simple example to keep in mind. So this is what is a convex function. So yeah, I should say maybe it's not, so I just say convex function like many other people, but it should be like strictly uniformly convex. Okay? Uniformly, it means that, so this is the convexity bound is independent of the point where you are, and this is this has to be strictly positive definitive. Okay? I will say it very quickly. So, but these are not generic convex or quasi-convex function. That's a problem. So here's an example of convex function. That's really the one you keep in mind. And here an example of quasi-convex function, the one also you keep in mind. So here it's just a sum of square. Here it's a sum of square plus I put one linear term here. Okay. So this is the example to keep in mind. Now, steep functions are generic. Oh, was a good question, exactly this. So they are generic in the sense that, well, let's say that among smooth functions, the complement is like, well, it's like infinitely degenerate, I would say. So here's a more precise statement. So if you take a point such that has non-zero gradient, so if H is not steep in any neighborhood of I, then the coefficients of the Taylor series of H at this point, they satisfy many independent algebraic relations. Okay? So it is steep in this sense, in the sense that if you want the complement of non-steep, so you have to be careful how you state this, how you speak about this genericity, but it's certainly generic in a large sense. Okay? Now, if I come back to the theorem that gives me this small variation for a long interval of time, or for this effective stability, so this is effective stability, and I can say it's exponential stability because I have, this is the dominant part. Okay? It's stable for an exponentially long interval of time. So this condition of steepness is not optimal for effective stability, so you can ask much less about small h and still have this type of result, including results with exponentially long interval of stability. So there's a conjecture, so I made a conjecture some times ago, that H is effectively stable if and only if F is rationally steep. So not spend too much. So I have to introduce a bit this definition because it will be related to what I'm going to speak about after. So what is rationally steep? As I said, you just replace vector subspace by rational vector subspace in the definition of steepness. So our recall definition of steepness is that when you restrict your functions to any affine subspace, then it has only isolated critical point. Now, we replace vector subspace by rational vector subspace. So what is a rational vector subspace? It's a vector subspace which has a basis of vectors with integer components, or with rational components. It's the same thing. Okay? So if you do that, you say maybe, well, it's not so much difference. It makes a big difference, actually. It makes a big difference. But so it's still not known. It's known in some cases. any case. So what I'm going to say is that this rational steepness is related to this. I mean, there are some directions which are known in some cases, and well. So that's the restriction you have on Arnold diffusion. Okay, I will stop with them now. It means that for a lot of solutions, for most solutions, this cannot happen. And if this happens for some solution, it will happen after after a very long time, depending on, of course, the assumptions you have on small h, and depending on the regularity, for example, if in the long time in the analytic case. Or I will give later. Okay, I will give later. Yeah, because for the moment it's just. Okay, so that's the restriction. Now let me come back to the conjecture of Arnold. And so, what is known about this conjecture? Okay. So first of all, it starts with Arnold. Sorry, there's a mistake. I don't know what 60s. Sorry. So what Arnold proved? He proved the weak instability. So if you remember when I said there was an instability in the sense of Arnold that says that you can connect this kind of almost transitivity, and that was this weak instability. You say I can find one solution which like moves like a drift. It's much weaker. So what Arnold proved is that he proved you can have this weak instability for n equal 3, for one h quasi-convex, and for a specific f. If you compare this to the conjecture, it's very little, but still he made the conjecture that he made his conjecture. So that's what he did, and actually it took a long time to understand that. So he explained how to do, maybe, because he didn't really do it. He said, so you should do like this. It was enough, but it took a long time for people to actually even build, fully understand all the details of this. So then later you had various improvements. So still weak instability for, but this time of course for any n, for any h quasi-convex, convex now, okay. Still for a specific h, so just one example of f here, and any h but quasi-convex. Still have this assumption here. And also you have very precise estimates on this star with epsilon. So this appears when I define the drift. It's the time you need to wait until you actually have a drift which is independent of epsilon. Okay? And in this case, so you have this capital T of epsilon, that's the time of stability which appears in the Nikoroshev theorem. So in the quasi-convex case, you can they almost match. So you have like a very precise understanding of the transition from, let's say, from stability to instability in this case. Okay? So now I have to wait a long time. So until recently, you have results for more than one f at least. So let me say that. So this is due to Patrick Bernard, Vadim Kaloshin, and Ke Zhang. So they still prove weak instability for any n, okay, for any h, but still quasi-convex, okay, and a typical f. So a typical f is related to condition that Mather introduced, because Mather made an announcement about this conjecture of Arnold already some times ago. So this typical f, so Mather called it cusp generic, but have to be careful that it's not generic in any sense. Okay? For example, it's not even dense. It's not even dense. Okay? So I will not define it because it's a bit long. But still, it's more than one example, and it's a large class. Okay? And it's really non-trivial. Mm-hmm. So now even more recently, so this was just weak instability again. Okay? Now finally, now instability in the sense of Arnold, in the sense that appeared in the conjecture, then it was, let's say, announced in the case where n equals 3, h quasi-convex, and a typical f, so essentially the same typical f as here. So of course you have more condition here, but this defines the same set of cusp residual perturbations. So you have preprints by Kaloshin and Zhang, by Tieng, and announcement by Marco, and of course by Mather. I mean, all these here and also here strongly uses work and idea of Mather. So this is, I will not say this is the conjecture of Arnold, so because, well, you don't have still a generic F, but, well, this is, as I said, still a large class, really. But the problem of all these results, okay, is that you only have convexity everywhere. Okay? This only works if H is convex or quasi-convex. If you don't have this assumption, basically you don't know how to do, you don't know anything, so almost anything. So I will come to this point, and it's related to the conjecture of Arnold, how I stated, because you Arnold require a generic H, and in fact, for what matters, it can be true for any H. Okay? Of course, you have to restrict the perturbation, but it might be true for any H, so you don't know. But the problem for the moment, the problem I'm interested in is how to go beyond this convexity, this quasi-convexity. Okay? Let me go back to that is instability in the sense of Arnold. So this is what he wrote, this is what I wrote, this is what some other people wrote also. And this is weak instability. So here you just have one solution that moves from its initial condition from some constant independent of epsilon. And here you have much more. If you give in any two, you can move very far, in all directions, basically. So that's the difference. Okay? Or if you want instability, some kind of weak transitivity with certain restriction. This, yeah, reformulation, I don't know if it's equal. It's not so precise what is written here. So, but this is what at least people will call the Arnold conjecture in this case. So let me go back to. So this is. So what I was saying is that if you take all the results, of course there's a lot I didn't give all the. There's a lot of results. And, but they all deal with convex or quasi-convex Hamiltonians. So now we want to go beyond convex Hamiltonian, at least if we can say something about that. So I'm also interested in this type of, so you have various, so for example, if you take Arnold non-degeneracy, it's generic, Kolmogorov non-degeneracy, it's generic also. Steep is generic, so you can try to go in many directions. Say, okay, I want to consider a larger class. So I will go right now that I will not be able to do that. But at least you try to go to a wider class, and you need to know in which direction you want to go. You have many directions. So since I'm more interested also in this Nekoroshev theorem, so I will try to go to this class of steep function. Okay? So first attempt is that try to deal with steep non-convex function. Okay? You can try. So here's the questions. The question is that find one example of H steep non-convex, one example of F, so that this has unstable orbits, so like weak instability. So the question is that even one example is not known in this case. You cannot even produce one example. So perhaps let me give you the simplest steep non-convex function. This is this one. You can check it's steep. It's non-convex. So it's almost like the quasi-convex function, but I put a cube somewhere. Okay? So this is an example. Okay, you can put n equal 3 because, of course, you can make silly perturbation that only involves these. So this is not the game. The game, you have to consider these parts. So this is really the simplest steep function non-convex, and it's not known. I don't know how to do that. So there's a big gap here if you try to deal with these functions, and perhaps I could stop here and say, I cannot do that, so it should work and try to do it, but, for the moment, for the moment it's not possible. I don't know. We don't know. Okay, so since you cannot even deal with the simplest steep function, which is non-convex, then try to remove them, because for the moment we cannot say anything. And go to the rationally steep case, for example. Rationally steep, non-steep function. So now I will give example of what is rationally steep, for example. So here's some example. You can consider linear Hamiltonian. So a linear Hamiltonian, if you take the definition of steep, it's never steep, actually. But it can be rationally steep. In this case, you take so this is just the scalar product, the inner product of a vector alpha with I, and assume that alpha is an irrational vector, okay, or a non-resonant vector. In this case, it's steep. Okay? This is a steep function, because if you, it will involve projection of alpha, onto a rational subspace, and if alpha is irrational, this is always non-zero. Okay? So, but this is like a bit cheating, maybe this example. Let me give other example. You can take like non-linear Hamiltonian, this guy. If you take a quadratic Hamiltonian, this is a symmetric square matrix, so this is still the inner product, with an irrational symmetric matrix, so I will not say what is your, maybe you can guess what is an irrational, no, maybe you cannot. So let me say that, I would say that, so A is a, like this, or maybe symmetric. So I would say it's irrational, which means what? It means that for all k, so I don't know, maybe I will make a mistake in one sense. So for all k, sorry, in mn, so for all matrix of times of size mn, okay, it's not square matrix. So maybe I will wrong. Oh, I don't know what. I'm not saying who is m, who is n actually. So the condition will be like this. We'll ask for the determinant of k a transpose of k. So if you put in the correct sense, it should be a m by m matrix, and you assume that it is non-zero. And then, I mean, then you can have like some type of Diophantine condition if you assume a bound on the absolute value of that with respect to the norm of k. Well, I mean, this is what is in a rational matrix. So you can try to deal with this case. So as I said, stability, now not in this example. In this example, stability. So these are rationally steep function, and in this case you can prove, so in this two simple case, I mean this one is very simple, this one is more complicated, but you can prove that stability, but in general it's still conjectural. It's a matrix which has m line or m row and m times n matrix. Oh, sorry, I forget something. Matrix in like this, with integer entries. So it's supposed to represent a vector subspace of Rn, which has of dimension m, which has a basis with integer coefficients. Okay. So sorry, it's coefficient in z. Okay. And this is the condition you ask. Under this condition, you can. If you take a diagonal matrix, it's a bit more easy to write. If you take a diagonal matrix, for example. Okay? Or, I mean, if I want to, for example, to give a simpler case, if I take A is just of the form 1, 0, 0, and alpha 1, if I take this, okay, I'm asking that to be, the condition is that let me put it n times. Means that alpha is not the square of a rational. In this case, that's what it means. And then, for example, a type of Diophantine condition will say that if you are given a p of pq like this, square of a rational, then you can control the distance of alpha 1 to square of rational, not just rational, but square of rational. In this simple case. So that is. Yeah. Yeah, exactly. No. No. But if it's convex, it's always true, this, if it's convex, you know? If it's convex, I mean, you can put, I mean, let me think. I mean, if A is positive definite, so everything is well known in this case from what I'm looking, so I want to avoid this case. So, for example, here, let's say here that maybe I will, I will ask. Wait a minute. Maybe I put it different. So I put alpha square. Well, I should assume so for that it's non-trivial that it does not have it's negative, for example. It does not have the same sign. So it's not positive definite. Assume that it's negative alpha 1. For example, and you require that. If alpha 1 is positive, so this is positive definite, I have nothing to say, okay? So I'm not assuming any sign here. I have to say, so yeah, I can put this in full generality, it's correct. But otherwise, you just say that this is negative, and or you put a minus and you put a square to say it's negative, and well, I mean, try to do something like this. Okay, so this is So now let me come back. Oops, sorry. Yeah. Stability in general is just a conjecture, except in this case. Now, if you want to prove diffusion in this case, or instability, you can construct specific example, in this case or in this case, with like very precise time of instability. I mean, here instability most of the time will be the weak instability, okay? Just the weak, just the drift. Huh? So everything is weak. Yeah. So you can construct specific example such that this has unstable orbits. Okay, you can. So it was done. I mean, I did it some time ago. But generically, so we don't know. So at least in this case, it's a bit better than this one because in this one you already don't know how to construct one example. And it's yeah, and well, I don't know why, but you cannot. So at least in this case you can, but generically I don't know. Okay. So we'll still continue to reduce. Because so I reduce, now I'm reducing again. So basically I will remove rationally steep function. So at the end I just have functions which are not rationally steep. So this is the class of non-convex Hamiltonian. So this class, so I will comment on that. So this class of non-convex Hamiltonian, they are not just non-convex, they are non-steep and they are non-rationally steep. Because this case already causes some trouble. So as I said, we are left with Hamiltonians which are not rationally steep. And now let me define the class of function. I will be interested in the rest of the talk. So I consider integrable Hamiltonian. So H, so this is a ball in Rn. So this is, I assume that there exists a line, L, so one-dimensional subspace, which is rational. So we put it like this, a line which is generated by a non-zero integer vector. And a closed segment in this line, so because I don't need all this line, a closed segment S in here, sorry, yeah. A closed segment S inside L, okay? Such that H is constant on S, okay? So clearly you see that you already remove convex function, you remove steep function, also because if you consider the restriction of H to this line, then actually your closed segment is a segment of critical point for this restriction. So clearly non-steep, okay? And I have an assumption also, this one is, in generality you can remove, I guess, but so let me put it here. And there exists a segment S star, because if you don't have this, that's very degenerate. There is the segment, subsegment S star in S, such that the gradient is non-zero on this segment. Of course, for this you just assume that this gradient is non-zero at one point, and then you find some little interval to this point, but, well, just a bit to simplify this one. You don't need it, actually. So these are the class I will consider will be the Hamiltonian that satisfy these two assumptions. So I called it S because sometimes this is called like a superconductivity channel. I mean, as you can guess, this at least this was introduced like this in some work of Chirikov, because superconductivity means along this you can drift very fast, actually. That's what is suggested by that. So if you consider this Hamiltonian, such Hamiltonian I will give example. Such Hamiltonian are degenerate in the sense of Nekoroshev, that's clear. In the sense of Arnold also, that's clear. You know? But they can be non-degenerate in the sense of Kolmogorov. Okay? We'll give example which are not, which means that for this example you can still have many invariant tori. They are not inside the same energy level, but still have many of them. But they are degenerate in these two sense. Okay? So of course I didn't want it to come to this, but all I tried before and cannot. So I end up, actually I tried to go beyond convex function to understand what happens to a wider class, but you end up to a smaller class actually. But it's a different class actually. It's a different, and we'll explain what are the difficulties also in this case. So let me give one example. So one example, you just take this one, you assume that you have something which is non-degenerate but non-positive definite or non-negative definite. So you take a difference of square, then you put whatever you want at the end. Let's say it vanishes at 0. So this I said it satisfies A1, A2. For example, you can choose, so you have a choice of line. Either you did two diagonal, either you take I equals plus or minus I2 and you put the rest equals to 0, for example. Okay. Well, in this case, so as I said, in this case, these are not degenerate. So you can have instability already starting for n equals 2. Okay. So already, I mean, the main point, what I'm really interested in is in type of behavior associated to this Hamiltonian, okay, non-convex. So you take L plus, L minus, so you have a choice of sign here. You choose what you want. Take S, any segment here, and S star, so S star is like this non-degenerate channel. You take any segment not containing the origin, okay? So that's a prototype of example of this. I mean, we're interested in this type of behavior, and so this is the class of function we end up with. Try to. So now let me. So what I said is it's still in progress because we have a conjecture. We cannot prove full generality. I will say what we can prove out of this, which is the simplest case in the moment. But so let me state the conjecture in this case, which. So okay, let me state the conjecture. You take R sufficiently large. You take H or be of class CR, so it can be for R not so small, but of course it can be analytic, whatever. Satisfying these two assumptions, A1 and A2. Then, so I will put it in the style of R not given any 2 point, I prime and I second, but in S star. So I recall S star is essentially like S, so it's a rational segment if you want. But I'm assuming that this is non-zero along this segment, okay? So for any 2 point here, this system has a solution for which the initial condition starts epsilon close to the first one. It ends, I mean, after some time tau, it's epsilon close to the second point. And also, I'm assuming that this time necessary to move this is of order 1 of epsilon. So I'm assuming that this is the fastest possible time. Okay? So if, for example, if in the case of conjecture of Arnold for convex system, so this should be exponentially. Okay? In our case, I mean, don't need in all the conjecture for generic, I mean, statement or conjecture for generic perturbation, don't ask the time you need to go from there. Here, I want the time to be exactly this one. Okay? So provided epsilon is sufficiently small and F, so F is of class CR, I put a 1 here to say it's the unit sphere in this class of, in the space of CR function. Okay? Consider F of norm 1 so that this is actually, the size of perturbation is actually epsilon. Okay? Is generic, and in this case, well, you can hope for an open and dense set, for example. Okay, I will give this statement instead. And moreover, I mean, the orbit shadows this, this segment here, okay, for all time. So if you compare to the conjecture of Arnold, so it's for a class of function A1, A2, so this is a degenerate class, okay? But this is at least non-convex. That was the point. That's the only thing we are able to do for the moment. And so, of course, here you have this segment. It is like a distinguished direction in which you can go. Okay? In the conjecture of Arnold, you have no, so you say you can go from one point to the other. Here, with these times, it makes only sense in this direction. Okay? So you're assuming I have one orbit that goes from here and goes until here. Okay? So, of course, as before, I had instability in the sense of Arnold. I have weak instability. So here it's a kind of instability for this type of system. And you can ask for a weaker instability, as before, just a drift along this segment S star. You just ask for a small drift. You cannot maybe connect any 2 point, but you just ask a small drift. And you have a weaker conjecture. Okay? You can make a weaker conjecture. So now let me give some statement. The statements are valid only for n equals 2 for the moment. That's the only thing we can deal, for sure, the only thing we wrote. So that's the first, like in the convex case, you start with n equals 3. Here it starts with n equals 2 because they are not degenerate. Okay? So the theorem is that for n equals 2, the weak conjecture, so not this one, but the weak one, just the drift, if you compare it to before, is true. Okay? It's true, you need H to be of class C3, F to be in an open and dense set in the unit sphere of C3. Okay? So this is just the weak. And so now second theorem is that for n equals 2, once again, and if you assume just a potential perturbation, you just take a perturbation which depends only on the angles and not the action. So I will not explain how we have this restriction, but of course you should remove this restriction. I mean, if you're able to remove this restriction, then you will be able to go to any n also. That's essentially the same problem. I'll try to explain that later. Yeah, H is in satisfy A1, A2. Sorry? It says basically that you have a rational segment or rational line so that H is constant. Okay. It means if you have a quadratic form, you have some factor like this, basically, if you're just interested in quadratic form. But of course, does not mean it's not necessarily quadratic. But that's the prototype of things I'm interested in, for this type of stuff.
So, and this means this the concrete example. So you have like a some rotation one direction or some other in the other.
Sorry?
This condition.
Yeah.
And in the prototype Hamiltonian case.
Yeah.
What does it mean?
This condition?
Yeah. So
It means that you have a isotropic vector for the quadratic form. So I don't know how you say this. If it's related to the dynamics, I mean, I will give an example of how you can have diffusion in this case and how you generalize to the convex case.
no, but it's in the typical. You take a Hamiltonian.
Yeah.
They say, well, basically after Arnold basically everything is you have the toroid and they are twisting.
Yeah.
Velocity.
Mm-hmm.
So here, what does it mean? Having this condition compared to the
Here, so that's a condition that is very, I mean, this type of, so 2-degree Hamiltonian, it's non-degenerate in the sense of Kolmogorov, so you can apply Km, so it means that really the rotation vector varies in a good way. But it's not, so I don't know, it's not a twist condition. I mean, I don't know what you mean by twist condition, but.
exactly this is the point. When you have positive, it's like a twist condition.
Yeah.
So here is some toroid, they are moving like positively and the other are moving.
Yeah, okay. Yeah. But so this condition is natural, I mean, at least is important for many problems. For example, for Km theory, it's not important to have this. What is important is just to have that it moves, that is a local diffeomorphism, that not, for example, for a twist map, that it moves in one direction and one. So if what does it mean for, in this case, I don't know, except that it's, no, I don't have geometric meaning of this. I don't know. It just appears that as a problem, so of trying to understand this type of Hamiltonian. And the behavior can be very different in this case. So now let me come, so as I said, so now I have a few less than 10 minutes, I think, like 7 minutes. So now I'll try to give ideas of how you prove that, I mean, or how at some point you end up with this restriction, and how maybe you can go beyond, but, well, not done for the moment. So let me give some ideas of the proof. But the proof is not so complicated, at least the strategy. Basically, the strategy is to reduce to an example, and an example you can do it easily. You know? But, I mean, of course, you cannot reduce that easily to the example. So for simplicity, I will consider just this one, because it already happens for this one. It starts for n equals 2, but actually all the statements are for n equals 2. So if you take some change of variables, symplectic, I will put it in this form. Okay, it's prefer because now, so I put the line of this line where you are degenerate. I put to the I-axis, to the I1 axis and I2 axis. Okay, so and I choose L to be equals to I2 equals 0. Okay, so let me just deal with this example. So the first case is just an example. Just mean that if you can construct an example, at least, so first case, I assume that my perturbation F, which a priori depends on, so theta 1, theta 2, I1, I2, I just assume it depends on theta 1. Okay, you see it's simple. And I assume F is non-constant. So basically my non-degeneracy condition on F, on the perturbation, will be this type of non-degeneracy. So I have my perturbation, I will associate this perturbation, some average perturbation, and I will assume it is non-constant. So it's certainly so it's open-ended, I said, but it's generic in any sense you want. Okay? So I assume that F is non-constant, because of course if S is constant, I'm still integrable, so I cannot do it. I assume that there is one point such that the derivative at this point is non-zero. Okay? That is what means F non-constant. So now you just write the equation of motion. So if you put a plus here, then you will have theta dot 1 equals I1, theta dot 2 equals I2. Now I have I have this, so now it changes the thing. You know? I will explain. So I just write the equation. Okay? This is the equation of motion. So since it does not depend on theta 2, here it's 0. It does not depend on I1, I2. It's just the derivative of this. So derivative of this with respect to I1, it gives me I2. and on the other way around. So that's the equation of motion. Yeah, it's not complicated. Now I'll choose an initial condition. I choose theta 0, I0, so my initial condition. With, so I2 of 0, I want to be equals to 0. So I take it equals to 0. And I take my initial theta 1 equals to this point here, theta 1. And the other is arbitrary. Okay? Just choose this. And then you get easily that you have a... So what you get is that, so here the speed is equals to 0. So since I'm starting at 0, I remain all time at 0 for all time. So this is always 0. So now the speed of this is always 0, so I always stay at its initial position. Theta 1 equals always this. And now this is constant. Okay, this is a constant. But now f prime applied to this point is non-zero. So I have this. Okay, I can exactly solve I1 of t. It's I1 of 0 plus this. And since this is non-zero, well, it's, you are done for this case. Just an example. Hence, if you take tau proportional to this, then this can be made arbitrarily large. Okay, this drift with optimal speed, okay, or with an optimal time. Oh, that's just one example. So now let me go to a second case. Second case is just, okay, now I consider that I have epsilon f, now we'll call the f bar, it depends on theta 1 as before, but on I, this time, plus I have something epsilon square. Well, I don't need a square, but I need some power better than this. I mean, let's put square, f tilde, and a general term. So on here, I don't assume anything. I just assume I have epsilon square. And on this function f bar, I assume that for some point theta 1 star I1 star, I have that the derivative of this function with respect to theta 1 is non-zero. Okay? This is what I assume. Now, okay, in this case, we are close to the first case. Of course, here I have dependence on I. Here I have a reminder. But so what you can prove is that before I2 of t always gets stuck in this line, in this resonance. It was blocked in this resonance. Now it's not necessarily blocked, but it can oscillate, not too much. So I2 of t stay epsilon close to 0 for up to this time scale. And, well, this is sufficient to prove that if you choose tau proportional to that, you have a drift. Okay, well, that's it's not so different. So everything is easy. Now, general case. Now you come to the general case. Now, by normal form and averaging theory, well, what you can do is that you can find a symplectic transformation, epsilon close to the identity, such that if you change variable, you are exactly like in the second case. Okay? And this is the f bar of the second case. So I don't write what is the f tilde of the... So you are exactly like this. You reduce your perturbation to this. And f bar is this. Okay? So now you might say, okay, now it's finished, you have win. So, well, in fact, there's a problem, of course, at some point. This is the problem, and you cannot overcome this in general, I guess. So the issue is that this transformation you get is only locally defined. So it's defined on some small domain, which is epsilon dependent. So, which means that this, you actually see this perturbation, but on an epsilon domain. So if you want to drift independently of epsilon, you cannot use that. Okay? So that's the problem. The problem is that this transformation only makes sense in epsilon domain, and so if you want to have a drift orbit which moves, you cannot move more than something which depends on epsilon. Okay? So I put it like this. And in general, the diameter, I mean the upper bound on the diameter of this domain, it goes to 0 with epsilon. So basically what I said before is useless if you just have this. Okay? Now in some cases, so that's the problem. Now you have to work in this case. So in some cases, for example, if n equals 2, you can work more and try to construct a phi in a different way, such that it has which has a domain which contains, whose diameter is, of course, is always independent of epsilon, his diameter, but when epsilon goes to 0, the diameter does not go to 0. I mean, on some large domain. I guess not very clear, but what I say that here, in general, it's only the diameter goes to 0 with epsilon, and here you can make a construction on some large domain, on some domain of order 1. And in this case, we can use the previous easy argument once you know how to do that to prove it. So there's some cases, I don't know which, all of them, but certainly not in all cases. It's not possible. For n equals 2, it's easy. For some of the cases also it is, we can do, but not in all. In all cases, I don't think you can. So that's the issue. Now, in general, what it gives you, so that's basically how you can prove the statement for n equals 2. And the non-degeneracy comes from the fact that you ask for this function, once you fix I to be like non-constant dependent theta, and you can easily prove that it satisfies for an open-ended set. So in general, this argument, I mean, when you cannot improve here, you cannot improve the transformation, this only gives what is called, I would say, micro-diffusion. It means you have actually a drift, so you can actually have a lower bound on the scale, but it's just square root of epsilon. Now, in general, in the convex case, is that, or in the case where you can prove diffusion, actually it always goes like this. You can like make a small drift. You just make a small drift. But then you can also make small drift, and you can match all the pieces together to have a large drift. Okay? And for this, you have tools. So for the average Hamiltonians, you have a lot of structure. You have some invariant sets, so defined by action minimizing properties, or defined by some hyperbolicity properties. And you also have tools to shadow, because now you just read little pseudo-orbits, and you have tools to shadow them. Here, you don't have any tool, actually, to shadow. So you can do, but so we are hoping that with some more condition, to explain, we can maybe try to pieces this small drift, because this small drift is the only thing we can do from this argument. Okay. So, and I'll stop here. Okay. Thank you.